All right, so now we are in section 3.8, and again, we're still looking at applications of derivatives here. It turns out, though, in this section, we're not really going to be taking a lot of derivatives in the work that we do. Instead, what we're going to be doing is looking at how the derivative applies to some concepts you've probably already seen in previous classes, specifically applications involving exponential growth and decay. There's a lot of applications where this concept applies, and in an Algebra 2 class or a pre-calculus or college algebra class, you explore these in a pretty great amount of depth. But you don't do it using the terminology of derivatives because you don't have those tools yet. So now what we're doing is we're kind of taking a look back at those concepts that, again, you've probably seen already, but framing it in terms of derivatives. So to understand the jumping off point that we're going to take in this section, you need to know what a differential equation is. Now, differential equations is one of the, this is kind of subjective, but one of the biggest topics in mathematics. If you've looked at our course catalog, you'll notice that we have an entire course in differential equations, and that's only an introductory course that barely scratches the surface. I teach that course. I have a playlist on my YouTube channel of that entire course, so if it's something that you're interested in looking ahead at, by all means take a look. But the concept of a differential equation is not really something we're going to go into much depth at all in this class. In Calculus 2, you start taking your first real look at differential equations. But we need that concept here because we're going to be working with one very, very simple differential equation that guides the rest of the work that we do. So what is a differential equation? A differential equation is any equation that involves the derivative of a function somehow. The equation can be very, very complicated or very, very simple, and it can involve a lot more than just a derivative of that function. First of all, the derivative that occurs in the equation can be of any order. It can be first, second, third, whatever, nth order derivative. The equation can also involve other orders of that derivative. It can involve the function itself. It can involve the independent variable. It can look like a whole lot of different things, and we are not going to even start looking at all those different types here. That's not really what we do in this class. One particular differential equation, the one I'm about to talk about right here, however, is very, very useful in a number of applications. So we're going to start by thinking of this in terms of population growth, which we talked about in the previous section. And then we're going to see that this particular differential equation applies to a lot more than just that one example. But for this, let's suppose that we have a population of some species, some type of organism, and the function y equals y of t represents the number of individuals in that population at time t. So this is similar to what we did in 3.7. Now, without doing, too much analysis, one could reasonably come to the assumption that the rate at which this population will grow is proportional to the size of that population at any given time. And the reason that's a reasonable assumption to make is because the larger a population grows, so the larger y is, the more members of that population are present that are capable of reproducing. And so you have more reproducing pairs, which means the rate at which the population is increasing is also going to get larger. Okay, so as the population size increases, the rate of growth increases as well. And if we assume that that's a proportional relationship, then we can summarize that mathematically by this. dy dt equals ky, where k is understood to just be some constant of proportionality. This is a differential equation. Notice that it's an equation because there's an equal sign here, and it involves the derivative of some function y. Notice it, in particular, it relates the derivative of y to the actual function y itself in a specific way. The derivative of the function is just equal to a constant times the original function. Now, if you think about it, we've encountered a function that does something like this. So we'll talk about a solution to this equation in a second. But the equation here can mean something drastically different depending on the sign of this k here, whether k is positive or negative. If k is positive, then we refer to this differential equation as the law of natural growth. And why we call it that because k being positive and y would also have to be positive. Remember, y represents the number of individuals in a population. There's no logical interpretation of a negative value of y here. So y can only be non-negative. So that means that this would be non-negative, which means the rate of growth is also non-negative. As y increases, dy dt also increases. And that indicates growth in the population. If k is negative, then k times y would also be negative, indicating that my rate of change, my rate of growth is negative. In that case, I wouldn't think of it as growth at all because the population would be getting smaller. And so we call that the law of natural decay whenever k is a negative number. Now, when you have a differential equation, just like in algebra, when you talk about equations, we oftentimes want to know what the solutions of that equation are. The difference between a differential equation, though, and an algebraic equation is when you solve an algebraic equation, you're looking for numbers that act as the solutions to that equation. So, for example, a quadratic equation may have up to 2 solutions, which would be numbers. They would be real or complex numbers. Differential equations, the solutions are not numbers. The solutions are entire functions. Because remember, y is the unknown here, and y doesn't represent a number. It represents a function, in this case, a population function. So what we are looking for here is a function that would satisfy this. What is a function whose derivative is equal to a constant times itself? Okay, to find that, we don't have the tools for solving these directly. That's what a differential equations course is for. But we can verify with an educated guess what a particular solution might look like. Y equals c e to the kt. That c is some constant. E to the kt. The k here is the same k that's appearing here. This would be a solution to this differential equation for any value of c. And the way we can verify that is by taking its derivative. dy dt is equal to, now this is a constant times an exponential function, and using the chain rule, the derivative of this would be c times k e to the kt. But if we rearrange some constants here, since it's all multiplication, and write that as k c e to the kt, well, the c e to the kt in parentheses here is exactly the function that we were starting with in the first place. So we could call that entire thing y. Thus, this becomes ky. dy dt equals ky. That means it satisfies this equation. So we can't show this in this class because, again, we won't have the tools until midway through Calculus 2. But you can show that this differential equation will only have solutions in this form. So any solution to this has to take this form. And again, you're taking that fact for granted here because we don't have the ability to prove it yet. So that's useful. That means that the population growth, according to this assumption here, would grow exponentially because this is an exponential function. And we can do a little bit more than that as well. That c there, that mysterious constant c, actually tells us something useful about the function itself. Notice if I have my solution here, so y equals c e to the kt, that's the function that determines the population at time t. If I plug t equals 0 into this function, we think of t equals 0 as a starting point or an initial point in time. Then notice what I get is e to the power of k times 0, or e to the 0, which is just 1, and then c times 1 is c. So in other words, that means that y of 0 equals c, which means that that constant c that's appearing right here represents the initial value of that population. That's what we call it, initial value, the initial population size, okay? So we're going to summarize that as a theorem. The only solutions to that differential equation that we just talked about are exponential functions of this form. Y of t equals y of 0, that initial value of that population, times e to the kt, okay? Now, I mentioned before that this particular differential equation applies to numerous other cases. We're going to look at 4 of them in total today. Looking a little bit deeper into this, the number k that appears here also has some important meaning. And again, particularly in the context of population growth. So again, if we're assuming that we're talking about a population function, instead of calling it y, let's call it something a little bit more relevant. Let's call it capital P for population. P equals P of t. Let's suppose that this function represents the size of some population at time t. My differential equation looks like this in the case of using a p instead of a y. dp dt equals kp. I can solve this for k, which would give me a quotient, k equals dp dt over p. That's the rate of change in my population divided by the size of my population. That ratio right there can be interpreted as a relative rate of growth. It's the rate of growth of this population relative to the size of that population. The result of this thing is going to produce a decimal, which can be interpreted as a percent. Specifically, this quantity, this relative growth rate, is telling me the percent rate of change in my population. Okay? So to give you an example to sort of understand that, if we have a value of k equal to 0.07. So if I have this specific differential equation representing the population growth model that we're talking about, that 0.07 is the relative growth rate of this population relative to its size. So that means that the population will grow by a rate of 7% of its size per year. Okay, that's essentially what that's talking about. So let's get into an example now. In this one, we're looking at a bacteria culture. That's the type of population we're investigating. It says a bacteria culture grows with a constant relative growth rate. The bacteria count was 400 after 2 hours and 25,600 after 6 hours. Bacteria grow and replicate very, very quickly. So this population is going to grow very, very rapidly. The fact that it says a constant relative growth rate indicates that, where is it? Oops, that's the wrong page. I'm on the other side of it. It indicates that this is true. dp dt over p is a constant, which we could set equal to k. Multiplying both sides by p indicates that we're looking at a differential equation of this type. And according to this theorem up here, that means that we have a solution of this type. Okay? So for part A, what are we asked to do? We're asked to find the relative growth rate. So what we know, based on what we just recapped on, is that this population, this culture of bacteria, has a population function that we can call y of t, and it's going to be equal to y of 0 e to the k t. Now, in this equation here, in this function, there's two unknowns. We don't know the initial size of the culture. Notice part B is asking me to find that. And we don't know the relative growth rate, k. T is the input for this function. It's whatever I want to plug into it. So the two unknown constants are the y of 0 and k. I don't have either of those given to me in the problem, but I am given other information. We're told that the bacteria count was 400 after 2 hours. So that means I would have a total of 400 bacteria in this culture at time t equals 2. So if I plug a 2 in for t here, that becomes 2k. And then I'm also told that we have 25,600 bacteria after 6 hours. So doing something similar there, I would have a total 25,600 bacteria after 6 hours. Plugging a 6 in for t gives me e to the 6k. Now what I have here is a system of two equations with two unknowns, the y of 0 and the k. And we know that in general, we can usually solve systems of two equations in two unknowns. Now, these are not linear equations. So I can't necessarily do what I would do in like an Algebra 1 class, solving linear equations. They are nonlinear, but that doesn't mean we can't solve them. We just need to use different techniques sometimes. If I take this equation and divide it by this equation, meaning take this number, divide it by that, set that equal to this expression divided by that expression, I would get 25,600 divided by 400 equals y of 0 e to the 6k over y of 0 e to the 2k. My reasoning for doing that is because now the y of zeros cancel out and I don't have to deal with that second unknown anymore. On top of that, these exponential functions simplify. I just subtract their exponents to get e to the 4k. Okay? Now this guy right here, if you do the division, comes out to a nice whole number. That's equal to 64. Okay, so what I have is 64 equals e to the 4k, and the goal here is to solve for k because that's my relative growth rate. So that implies that if I wanted to solve this, to solve for k, I would need to take a natural logarithm of both sides. So I would get that the natural log of 64 is equal to 4k, or k is equal to the natural log of 64 divided by 4. You go ahead and plug that into a calculator and you're going to get a number that's approximately equal to 1.04. Now we write it as a decimal, but you can think of it as a percent. Okay, notice the time is measured in hours here, so we can think of that as a relative growth rate of 104% per hour. So with that, let's leave that there. Part B is asking us to find the initial size of the culture. That's y of 0. So to find that, what I can do is go back to either of these two equations here and plug in the value of k that I got. And then use that to solve for y of 0. So let's maybe do this first equation. It looks slightly simpler. I would have 400 equals y of 0 e to the 2 times 1.04. Okay, so solving for y of 0 means I want to divide both sides by that exponential right there. So I'm going to have 400 over e to the 2 times 1.04 would be 2.08. And again, that's going to go into a calculator as well. What we get is approximately 50. I think it's like 49.97 or something, but rounding is appropriate here because, again, we're talking about something that's discrete. Remember, y represents a number of bacteria, and for our purposes, we would never consider that to be a fractional amount. That's always going to be some whole number count of bacteria. So 50 is a more reasonable answer to get than 49.97 or whatever it was. Okay, so that's going to be our initial size of the culture, what we start with at time t equals 0. Now let's move on to C. C is asking us to find an expression for the number of bacteria after t hours. We have essentially done that now because we've solved for the two unknowns in the original equation. I can write y of t equals 50, the initial amount in my population, the initial amount in my culture, e to the kt. K was 1.04, and that's times t. Now, I can leave it at that, but I have a little bit of an issue with the answer the way that it is. My issue with this is that the k that we found here, the 1.04, is a rounded amount. I plugged something into my calculator, and up until this point, I had an exact amount, but then as soon as I plugged it into a calculator and rounded, I'm now using an approximate value of k. And that might be fine for, you know, some small values of t here, but I kind of expect, if you consider how quickly exponential functions grow, as t gets larger and larger, I'm expecting this function to give me answers, to give me values that are further and further away from their correct values. So can we improve on this in any way? And the answer is yes, we can. Of course, otherwise I wouldn't be blabbing on and on about this. So here's an alternative way of looking at this. Here is our original function, right? Y of t equals y of 0, which is still 50. We're trusting that amount. E to the kt. Now notice e to the kt can be written this way. E to the k to the power of t. Okay, that's the same thing as e to the kt because I have that power to a power property. But what is e to the k? Well, K, even though I rounded it here, a step before that, I had a perfectly accurate answer, natural log of 64 over 4. So I'm going to write that like this, 50 times e to the power of the natural log of 64 over 4 to the power of t. Now what I'm going to do is use my power to a power property again, and think of this as natural log of 64 times 1/4, and then bring the 1/4 out here, so that this becomes 50 e to the natural log of 64 to the power of t over 4. Okay, I'm using exponent properties there. And can you see why I wanted to do this? The e and the natural log are inverses of each other. Those cancel out. So that gives me this. Y of t equals 50. In the parentheses now I have a 64. And this becomes t over 4. Even though this is technically correct, and if this were one of the odd numbered problems in your book, I have a feeling the answer in the back of the book would have given you this. They tend to just do the rounded thing. In my experience, you're going to get better results with this function because this one is not rounding anything. This is going to give me essentially accurate results. So finally, we have a part D to do. It says, when will the culture reach a count of 50,000? Okay, so for this one, I now have two functions I could use, but I'm trusting this one more, so I'm going to use this as my result, or this is my function. I want the count, which is this, y of t, to be 50,000. I'm going to plug 50,000 into that. Equals 50 times 64 to the power of t over 4. It says, when will that occur? Meaning we're solving for t. Okay? So divide both sides by 50. I'm going to get 1,000 equals 64 to the power of t over 4. Okay? Now what I'm going to do is take a log with a base of 64 of both sides. So I'm going to get log base 64 of 1,000 is equal to, the point of doing that is because that cancels this 64 out, so I get t over 4, or in other words, t equals 4 times log base 64 of 1,000. Depending on the type of calculator you have, you may not have a button for log base 64. No calculator is going to have a button for it, but like I think TI-89 calculators allow you to input this base using one of the functions in there. But in general, most calculators don't have the ability to calculate this log directly. So in algebra, we learn how to do this using a change of base formula. If you remember that, t is equal to 4 times, this logarithm can be converted to this. Log of 1,000 over log of 64. Okay? And I could have used natural log. This is log base 10. They'll both give me the same result. I chose log base 10 because I can evaluate log base 10 of 1,000 in my head. That's equal to 3. So this is equal to 4 times 3, which is 12, over log of 64. That needs to go into a calculator, and this gets me approximately 6.64 hours. Okay? In problems like this, I always like to go back to the original information that I was given and try and determine if this is a reasonable answer to get. So let's look at the amount that we're getting, 50,000. We know that after 6 hours, we've got 25,600 bacteria in this culture. 50,000 is almost doubling that amount, okay? Almost doubling that amount. Does that seem reasonable when I see this, that it took 6 hours to get to this value and only another 0.64 hours to almost double that amount? Well, that is actually reasonable. Because if you look at how much we have to start with, 400, over the course of only 4 hours, it way more than doubled, right? You double 400 and you get 1,600. And then if you double 1,600, you have 3,200. and it's going to be getting larger and larger in a relatively short span of time. So this culture is doubling in size very, very rapidly. And so it kind of makes sense that it wouldn't even necessarily take another full hour for this culture to double in size. This is a very reasonable answer to get based on the information that we have. Okay, so we have 3 more applications of the exponential growth and decay ideas to look at, and we'll do that in the next video.